Here, it would be a good idea to see if we can reduce the fraction, since the entire fraction is inside the root symbol. But 121 over t squared doesn't reduce as a fraction. There's no common factors in the top or the bottom. So the next thing is to rewrite the square root of a division as a division of the individual square roots. So we can bust apart the square root of a fraction into the square root of the top and the bottom. This top, the prime factorization of 121 is 11, so it breaks apart into the square root of 11 times the square root of 11. The bottom one breaks apart into the square root of t times the square root of t. And we get 11 over t. And we're done. Here we're asked to simplify, and we could simplify by trying to rationalize the denominator, but notice first that if we wrote this with one fraction inside one root sign, the 18 over the 2 would cancel to 9, and the y over y would just cancel to 1, and would have the square root of 9. And boy, oh boy, do I like the sound of that. So let's try it. Now that we have the entire fraction inside the root symbol, we can cancel. And as mentioned, 18 divided by 2 is 9. And the y's just cancel to 1, and so this is the positive square root of 9, which is 3. And that was a pretty slick way to do this. We're asked to simplify this and rationalize the denominator, and as always, I'm going to break apart the pieces. So I'm going to take the cube root of the numerator. I'm going to take the cube root of the denominator. Then I'm going to do the prime factorization. 5 is prime, but I can break apart the cube root of 4 into the cube root of 2 times the cube root of 2. Now it's time to create a plan for rationalizing the denominator. Well, that means making the denominator be a regular number, a root-free number like 7 or 5 or 3 or 2 or something. But do we have enough of these cube roots of 2 multiplied together to get a regular 2? And the answer is no. We need 3 of them. We need 1 more of them. So we multiply the bottom by 1 more because we want 1 more. And then since it's a fraction, we have to do the same thing to the top. Otherwise, we've changed the value of the fraction. Now on the bottom, we have rationalized the denominator because 3 like cube roots multiplied together make the thing inside. This exactly equals 2. And these are kind of the leftover bin up here. We've got a lonely little cube root of 5 and a lonely little cube root of 2, and multiplying those, we get a cube root of 10. So the most compact, simplified form with a rationalized denominator of this original problem is this. Here we're asked to do the same kind of thing, simplify and rationalize the denominator. So, since there's no canceling in 7a over 18, I would cancel first since it's a nice little fraction in there, but there is no canceling, so I'm going to see what kind of pieces we have. On top we have a square root of 7 times the square root of a. On the bottom we need to know what the prime factorization of 18 is. 18 is 9 times 2, and 9 is 3 times 3. So we've got a 3 times a 3 times a 2. Now I need to create a plan for rationalizing the denominator, which means make the denominator be a regular natural number, something like 7 or 2 or 4 with no roots. And this part is already just 3, just exactly 3. So what I need is a matching partner for this one. So what I need is a square root of 2. So I have to multiply the top and the bottom by the same thing, otherwise I change the value of the fraction. So on the bottom I'm now getting a regular 3 times a regular 2. On the top, these are all leftover parts, so they go in one big leftover root, in this case a square root. 2 times 7 is 14, and we have 14a. So we have the square root of 14a over 6. Notice you don't try to cancel the 14 and the 2 or the 14 and the 6, because that's not a 14, it's a square root of 14, and that's a completely different beast. This is the final answer.